Hello, and in this video we're going to look at Introduction to Exponential Growth by looking at a couple of your handouts. This one on the moon problem and the other handout that has exponential growth with these two problems here about a growing population in a city. So we're going to look at those two handouts. Start with the one about on the moon problem. So we're going to read through this. If you want to try this beforehand, these two handouts you can, and you can take a look at this video afterwards and see how you did. Right here, I'm going to read through this. It says, imagine that you have a piece of paper that's large as you need it. Imagine that you fold it once in half. How many layers do you have? Well, hopefully you have two. You fold it in half again, you're going to have 4 layers. You try this with a sheet and fold it again and again. It gets very difficult after the fourth fold or so because the paper gets really thick. Still, your imagination is great, so you imagine you can fold it again and again. You realize that folded paper piles up, gets thicker and thicker. Imagine a piece of paper approximately 1 millimeter thick. How many folds do you think you need before the top of the paper reaches the pile or reaches the moon? The moon is approximately 38,000 kilometers from the Earth, and you know one sheet is 1 millimeter. So this is going to grow exponentially because it doubles each time. You start with 1 and you go to 2, then you go from 2 to 4. So let's take a guess. What do you think your guess would be here? Write it in here what you think the guess might be. We're going to calculate that here in a minute. So what we're going to do that is we have to make sure we calculate how many, if we make up some way to create or add these folds till we get to this distance. Well, we have different units here, so we're going to have to convert 3,800 or 38,000 kilometers into millimeters, because each fold is a millimeter. So to do that, I'm going to use some unit analysis. I know that there's in 1 kilometer there's 1,000 meters, and in 1 meter there's 1,000 millimeters. So that means we'd have to multiply by 1,000 twice in order to get millimeters. So in order to do that, we would get we'd add 6 zeros to this, so it'd be 380. We already have 4 zeros. We'd add 6 more zeros. This is how many millimeters it is to the moon, approximately, from the Earth. All right, so since I don't have a formula for this, let's just use our calculator to try to figure out how many folds. This should grow pretty rapidly once you start folding over and you're doubling it. We should get a pretty rapid growth. So let's take a look at this. What we have here, and we're going to start with our first paper is our first fold. So first fold is 2 millimeters, right? First fold equals 2 millimeters. A second fold is 4 millimeters. And we're going to double each time. So let's take a look at this on the calculator. We're going to do, so this will be our first fold, 2 times 2. We get 4, that's our second fold. And then we're going to take that answer each time. I can use this calculator, just take the answer each time and multiply by 2, so we can double that answer by 2. So this will be the third fold would be 8, 4th, 5th, 6th, 7th, 8th, 9th, 10th. So in the 10th fold we have 1,024 millimeters. So that's just a little bit more than a meter, because we know 1,000 millimeters is 1 meter here. So in 10 folds the 10th fold is 1,024 millimeters. Let's continue on here. So we're up to this point on our graph, 1,000, or we've used up all of those. It's a little more than that. So we're just going to keep going. We're going to use this. So this is 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And 20 folds, we have 1, 0, 4, 8, 5, 7, 6. So over a million millimeters. So in 20 folds, we're up to a million. Okay, so we're getting closer. We're at this decimal place right here at a million. So we got to the 10th fold here, we got here, got to the 20th fold, we got here. So I'm thinking maybe 30 will take us here. That'd be a good guess. We jumped, but maybe we grow faster than that even, because it's doubling each time. So let's go back and try some more folding by just doubling the numbers here. Alright, so let's do enter again. So this is going to be 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So 30 folds we're at 1, 0, 7, 3, 7, 4, 1, 8, 2, 4. So we're at comma 4, 1. We're at 1 billion. So we're at 1 billion. So we're right here where I predicted we'd be. So we're close at 30 folds. So we're at 1 billion. All right. Okay, let's hit enter a few more times. We want to get to 38 billion. All right, so let's try that. We keep multiplying here. See if we can get to 38. Okay, multiply. That's 2. That's 4. That's 8. Okay, now we've moved into scientific notation. So I'm going to need to rewrite this in scientific notation so I can get that to be, so we can get comparable. Scientific notation means we move the decimal between the 3 and the 8, and we count the number of places that we get to there. There's 3, 6, 9, 10, 11. So we're looking for 3.8 times 10 to the 11th. Here we're at 1.7 times 10 to the 10th power. All right, so let's go back. This was 30. We're on 31, 32, 33, 34. We're on 34 now. 35, 36, 37. We're close here. 37. We're at 1 instead of 3.8. 37, 38. We're even closer. So at 39, we'll be past there. So 39 folds. We actually passed this by being 5.4. So at 39 folds is 5.5 approximately times 10 to the 11th power, which is more than this. So we reached there. We're at 270, or 2.74 at 38th fold. So it took 39 folds of paper to get to that point. All right, so we'll move on to our next worksheet, which is a calculation of population based upon growth. So in this one, population is increasing by 1,000 each year. So my first year would be 20,000 plus 1,000, or 21,000. Okay, and then I'm going to add 1,000 more. So here I would be 20,000 times or plus 2,000, so 22,000. So each time we're going to add 1,000. This would be 23,000, 24, 25 for the. This is a linear growth because we're growing by a constant value each time. It's linear, and we can actually write a formula for population here. Population is 20,000 plus 1,000 for each year X. So that would be my population equation. We could also write it in slope-intercept form by writing it 1,000 X plus 20,000 if you want to do it that way. So either way, that's the same thing, and we calculate out the thing by putting in the number. So if we put in 5 here, this should be 25,000. So it's growing linearly by the same constant. Now the other growth factor, what we're discussing in this class, is growing by a percent each year. So in this case, we're going to grow by 5%. So we're going to take 5% more. So we got 20,000 plus 20,000, or 5% of 20,000. All right, so that's going to be 20,000. I think of it as 20,000 times 1.05 because this is, you got a 1 here, and you can factor out the 20,000 and get 20,000 and 1 plus 0.05 here. We're growing by 5%, but we have to have the 100% of the thing also included. So in this case, the next calculation would be 20,000. Since we're growing by the same amount, 1.05 times 1.05. We're multiplying each time. All right, so we got 20,000 times 1.05 squared. And we keep doing that as we get down here. This will continue on, and we'll get down to 20,000 times 1.05 to the 5th power to be the actual increase. All right, so in this one, the population equation would be the same version that you see up here, except instead of 5 here, 5 is a year, our year is X here. So this would be our formula for that. This would give us a population each year after that. This is 100% of the population, but it's 5% increase. Now, if we were to write that same thing up here in this problem up here for the folding of the paper, we just say that it's growing by 2 each time. So that's 2 to the X. So our growth, this would be our growth, our folding, how much it is, it'd be 2 to the X. It's just that formula, because our starting amount there is 1 millimeter. So each time we get 1 millimeter, so it's 1 times 2 to the X. All right. Now that should cover those 2 worksheets. If you have any questions, you can send me an email.